Have you ever seen what sunscreen looks like under ultraviolet light? Not in person. Well, let me paint you a picture. Imagine taking a perfectly normal person, perhaps your friend, your partner, or even yourself, and applying sunscreen to half their face. To your eyes, the application is barely noticeable. Maybe there is a slight sheen or whitish cast, but otherwise it looks like regular skin. Now, switch to ultraviolet vision. Suddenly, half of their face transforms into an impenetrable void, a pitch-black mask that absorbs all light, contrasting starkly against the fluorescent glow of their natural skin. The division is shocking, almost alien. The sunscreen-covered half does not merely look different. It appears to swallow light itself, creating a visual effect so dramatic and uncanny that it seems to defy explanation. This is not science fiction. This is not digital manipulation. This is basic chemistry and physics manifesting in a way our human eyes normally cannot perceive. It is happening right now on beaches, in parks, and on the faces of millions of people worldwide who are protecting themselves from the sun. But why? Why does a seemingly transparent cream become an absolute void under ultraviolet light? The answer takes us deep into the invisible world of light, the remarkable evolutionary adaptations of plants and animals, the devastating health consequences of radiation, and ultimately, the ingenious ways humans have developed to shield themselves from a star that simultaneously sustains and threatens life on Earth. The story of sunscreen and ultraviolet light is far stranger and more fascinating than most people realize. It is a tale that spans billions of years, from the primordial chemistry that first protected ancient microbes to cutting-edge nanotechnology being developed today. And understanding it might just change how you think about something as mundane as applying sunscreen before a day at the beach. The year was 1800, and the world was about to expand in a way nobody expected. Wilhelm Herschel, a German-born British astronomer already famous for discovering the planet Uranus, was conducting experiments on solar radiation. Using a prism to create a spectrum of sunlight, Herschel methodically measured the temperature of different colored bands of light. He noticed something peculiar. When he placed a thermometer just beyond the red edge of the visible spectrum, where no light was apparent, the temperature rose significantly. Herschel had discovered infrared radiation energy beyond what human eyes could see. This revelation was profound. The visible world was merely a slice of reality, with vast regions of the electromagnetic spectrum extending invisibly in both directions. Just 1 year later, in 1801, German physicist Johann Wilhelm Ritter was inspired by Herschel's discovery. If invisible radiation existed beyond the red end of the spectrum, might there also be invisible radiation beyond the violet end? Ritter designed an elegant experiment using silver chloride, a chemical that darkens when exposed to light. He found that this substance darkened most rapidly when placed beyond the violet edge of the visible spectrum, in what we now call ultraviolet light. It appears hence proved, Ritter wrote, that beyond the violet end of the spectrum there exists invisible light, which possesses the chemical property of decomposing silver salts even more actively than violet light itself. These twin discoveries fundamentally changed how scientists understood light. The electromagnetic spectrum suddenly stretched far beyond human perception, with visible light representing only a tiny fraction of the radiation surrounding us constantly. Isaac Ramirez, a modern photophysicist at Cornell University, explains the scale. If the entire electromagnetic spectrum were stretched across North America, the visible light portion that humans can see would be roughly the size of a dime. Ultraviolet light would occupy just a few feet beyond that dime, but its effects on life are profound and far-reaching. This invisible ultraviolet realm is divided into 3 main bands: UVA, 315 to 400 nanometers, UVB, 280 to 315 nanometers, and UVC 100 to 280 nanometers. Each band interacts with matter in distinct ways, but they share a common characteristic. They all carry more energy than visible light, and with higher energy comes greater potential to interact with and damage biological molecules. What makes ultraviolet light so special, so dangerous, and so visually distinctive when interacting with substances like sunscreen? To understand this, we need to dive into the atomic world, where light and matter engage in an intricate dance of absorption, reflection, and transformation. But first, we need to address a fundamental question. How can we see something that is, by definition, invisible to the human eye? How do scientists, photographers, and even smartphone users capture images in the ultraviolet spectrum? Amelia Ellis stands in her photography studio in Portland, adjusting specialized equipment that few photographers possess. Her camera looks ordinary enough, but the modifications are extensive. The internal filter that typically blocks ultraviolet light has been removed, and in its place, she has installed a filter that does the opposite, blocking visible light while allowing only ultraviolet wavelengths to pass through. Most people think of UV photography as creating some kind of special effect, Amelia explains. But it is actually revealing something real that exists all around us, something our eyes simply cannot detect. The human eye has evolved to see wavelengths between approximately 380 and 700 nanometers, what we call visible light. This range is not arbitrary. Our atmosphere allows these wavelengths to pass through relatively unimpeded, while blocking much of the rest of the electromagnetic spectrum. Our visual system evolved to detect precisely the range of radiation that is most abundant in our environment. Evolution is practical, says Dr. Andrea Evans, an evolutionary biologist at the University of Michigan. Our ancestors did not need to see ultraviolet light to survive and reproduce, so we never developed that ability. But many other creatures did. Indeed, while humans are blind to ultraviolet light, many animals can see it clearly. Bees, butterflies, and birds all perceive ultraviolet patterns invisible to us. Flowers that appear plain yellow to human eyes often display intricate ultraviolet patterns that guide pollinators to their nectar. Some birds have ultraviolet markings that play crucial roles in mate selection. What appears to us as a uniform blue jay is, to other blue jays, a complex canvas of ultraviolet signals communicating health, fitness, and genetic quality. But back to Amelia's studio, where she demonstrates how to photograph in the ultraviolet spectrum. Her subject today is simple: 2 identical bottles of sunscreen, one labeled chemical and the other mineral. Under normal light, both appear white and creamy. But when photographed under ultraviolet light, they look radically different. The chemical sunscreen appears almost pitch black, Amelia points out. It's absorbing over 98% of the ultraviolet light hitting it. The mineral sunscreen, on the other hand, appears bright white because it's reflecting most of the UV radiation. This dramatic visual difference hints at the fundamentally different mechanisms these sunscreens employ to protect our skin, one absorbing dangerous radiation, the other reflecting it away. But before we can fully appreciate these mechanisms, we need to understand why ultraviolet light requires such elaborate protection in the first place. The answer lies in the deceptively simple relationship between energy and wavelength, and the precarious molecular structures that form the foundation of all life. There is an inverse relationship between the wavelength of light and its energy. The shorter the wavelength, the higher the energy. Ultraviolet light, with wavelengths shorter than visible light, packs significantly more energy per photon than the light we can see. This additional energy is what makes ultraviolet radiation both useful and dangerous. In the early 1900s, scientists began to understand that light behaves not just as a wave but also as discrete packets of energy called photons. Albert Einstein won the Nobel Prize in Physics in 1921 for his work on this photoelectric effect, showing that light's energy is directly related to its frequency and inversely related to its wavelength. Dr. Ian Reeves, a photochemist at MIT, explains the significance. A single photon of ultraviolet light can deliver enough energy to break chemical bonds in important biological molecules. Visible light generally cannot do this directly. Think of it like throwing tennis balls versus bowling balls at a house of cards. The tennis balls might bounce off harmlessly, but a bowling ball will destroy the structure. The most vulnerable house of cards in our bodies is our DNA. The double helix structure of DNA, while remarkably stable in many ways, has a critical weakness. It strongly absorbs ultraviolet radiation, particularly UVB light with wavelengths around 260 to 280 nanometers. When DNA absorbs this energy, adjacent thymine or cytosine bases can form abnormal bonds with each other, creating what are called thymine dimers. These dimers distort the DNA structure, potentially preventing proper replication and transcription. If the cell's repair mechanisms fail to correct these distortions, mutations can occur. Accumulate enough mutations in crucial genes, and cancer may develop. The link between ultraviolet exposure and skin cancer is one of the most thoroughly established cause and effect relationships in all of medicine, says Dr. Alicia Edwards, a dermatologist at Memorial Sloan Kettering Cancer Center. We can literally see the UV signature in the mutations of most skin cancer cells. This is not a minor health concern. Skin cancer is the most common form of cancer in the United States, with more than 5 million cases diagnosed annually. Each year, more Americans are diagnosed with skin cancer than all other cancers combined, and treatment for non-melanoma skin cancer costs about $4.8 billion annually. The primary culprit? Ultraviolet radiation from the sun. Over 90% of skin cancers are associated with UV exposure. This makes the sun both essential for life on Earth and one of our most significant health hazards. But humans are not the first organisms to face the ultraviolet dilemma. For billions of years, life on Earth has been developing strategies to harness the sun's energy while mitigating its dangers. These ancient solutions provide the blueprint for our modern sunscreens and reveal why they interact with ultraviolet light in such visually striking ways. The history of ultraviolet protection is as old as life itself. When the first primitive microorganisms emerged in Earth's primordial oceans around 3.8 billion years ago, they faced an environment far more hostile to unprotected DNA than our world today. The early Earth had no ozone layer, the protective stratospheric shield that now absorbs most of the sun's UVB and all of its UVC radiation. Early life evolved in water, which provided some UV protection, explains Dr. Isaac Richards, an astrobiologist at NASA's Ames Research Center. But even a few meters below the surface, enough ultraviolet light would penetrate to damage DNA. Early organisms needed molecular sunscreens to survive. These ancient microbes developed several strategies. Some produced pigments like carotenoids and melanins that absorbed ultraviolet radiation before it could reach DNA. Others evolved efficient DNA repair mechanisms. And some, particularly cyanobacteria, developed compounds that functioned remarkably similarly to modern sunscreens. Mycosporine-like amino acids, MAAs, sometimes called nature's sunscreen compounds, are among the oldest photoprotective molecules known. These compounds strongly absorb ultraviolet light, particularly in the UVA and UVB ranges, dissipating the energy harmlessly as heat. Found in numerous marine organisms, from bacteria to algae to fish, MAAs likely represent one of evolution's earliest solutions to the ultraviolet problem. As life evolved and became more complex, ultraviolet protection strategies diversified. Plants developed complex mixtures of flavonoids and other compounds in their outer tissues. Animals evolved protective behaviors, specialized skin cells, and integumentary structures like fur, feathers, and scales. Humans, with our relatively hairless skin, evolved a particularly elegant solution: melanin. Produced by specialized cells called melanocytes, melanin is a family of pigments that absorbs both visible and ultraviolet light. People with darker skin produce more melanin, providing greater natural protection against UV damage. When lighter-skinned people are exposed to sunlight, their melanocytes increase melanin production, creating what we call a tan, essentially, the body's attempt to create a natural sunscreen. But melanin alone is insufficient protection, especially for individuals with naturally lower melanin levels or those living in environments with intense sun exposure. Throughout history, humans have sought additional protection from the sun's harmful effects. Ancient Egyptians used rice bran extracts containing gamma-oryzanol, which absorbs UV light, notes Dr. Amanda Edwards, a historian of medicine at Columbia University. Greek women applied olive oil and powdered lead. Native Americans used particular plant extracts, while ancient Chinese and Japanese people used parasols and wide-brimmed hats. These early sunscreens were developed through trial and error, without any understanding of ultraviolet radiation or its effects. It would take the scientific revolution of the 19th and 20th centuries to transform sun protection from folk remedy to evidence-based prevention. The modern era of sunscreens began in 1938, when Swiss chemistry student Franz Greiter suffered a severe sunburn while climbing Mount Pisbin at the Switzerland-Austria border. This painful experience inspired him to develop one of the first effective commercial sunscreens, which he called Glacier Creme, Glacier Cream. The product had an estimated SPF of 2 minimal by today's standards, but revolutionary at the time. Around the same period, Airman Benjamin Green developed a substance he called Red Vet Pet, Red Veterinary Petrolatum, to protect soldiers from the sun during World War II. This thick, red petroleum jelly was uncomfortable and impractical, but it established the principle that chemical barriers could provide UV protection. After the war, Green improved his formula, eventually creating what would become Coppertone Suntan Cream. These early products were primarily designed to prevent sunburn, not to provide comprehensive protection against all ultraviolet radiation. Their formulations were crude by modern standards, and they often allowed significant amounts of harmful radiation to reach the skin. But they represented the first steps toward the sophisticated ultraviolet shields we have today. And with those sophisticated shields came the striking visual phenomenon we are exploring: the dramatic appearance of sunscreen under ultraviolet light. To understand this effect, we need to examine precisely how modern sunscreens work at the molecular level. Modern sunscreens employ two fundamentally different approaches to protect skin from ultraviolet radiation: organic, often called chemical, filters, and inorganic, often called physical or mineral filters. These two categories function through distinct mechanisms, which explain their dramatically different appearances under ultraviolet light. Organic UV filters are molecules specifically designed to absorb ultraviolet radiation. When an ultraviolet photon strikes one of these molecules, the energy excites electrons into higher energy states. This excited state is unstable, and the molecule quickly returns to its ground state, releasing the absorbed energy as heat. It's a remarkable process, says Dr. Isabel Rodriguez, a cosmetic chemist who has developed sunscreen formulations for major brands. These molecules essentially transform potentially harmful radiation into harmless heat, over and over again, thousands of times per molecule before breaking down. Common organic UV filters include avobenzone, oxybenzone, octinoxate, and octocrylene, each optimized to absorb specific wavelength ranges within the ultraviolet spectrum. Modern sunscreens typically contain multiple organic filters to provide broad-spectrum protection against both UVA and UVB radiation. The molecular structures of these compounds are key to their function. Most feature conjugated systems, arrangements of alternating single and double bonds that create extended electron clouds capable of absorbing specific wavelengths of light. These structures are carefully engineered to maximize absorption in the ultraviolet range while minimizing absorption of visible light, keeping the sunscreen transparent to the human eye. When viewed under ultraviolet light, areas covered with chemical sunscreens appear pitch black precisely because these molecules are doing their job, absorbing nearly all of the ultraviolet radiation rather than reflecting it back to be detected. Inorganic, mineral filters work differently. These sunscreens use mineral particles, primarily zinc oxide and titanium dioxide, which both absorb and scatter ultraviolet radiation. Unlike organic filters, which work through electronic transitions, mineral particles function more like tiny mirrors and sponges, reflecting, scattering, and absorbing ultraviolet rays. Mineral sunscreens have been used for thousands of years, though our ancestors did not understand why they worked, explains Dr. Adam Erickson, a pharmaceutical scientist specializing in dermatological formulations. Ancient Egyptians used zinc compounds, and white paint containing titanium dioxide has been used as sun protection by various cultures. Modern mineral sunscreens use micronized or nano-sized particles of these minerals to reduce the white appearance on skin while maintaining protective properties. Under ultraviolet light, mineral sunscreens typically appear white or reflective, contrasting sharply with the black appearance of chemical formulations. This difference visualizes their primary protection mechanisms. Chemical sunscreens predominantly absorb UV, appearing black, while mineral sunscreens largely reflect it, appearing white. Both approaches effectively prevent ultraviolet radiation from reaching the skin, but they create strikingly different visual signatures in the ultraviolet spectrum. The formulation of modern sunscreens involves more than just active ingredients. A typical sunscreen contains emollients, emulsifiers, thickeners, and preservatives to create a stable, pleasant-to-use product that distributes evenly on skin and resists water and sweat. Each of these components can also influence how the product appears under ultraviolet light, creating unique signatures that researchers and quality control specialists use to evaluate coverage and effectiveness. When we examine sunscreen application under UV light, explains Dr. Rodriguez, we can immediately identify gaps in coverage or areas where the product has been unevenly applied. This visibility in the ultraviolet spectrum is not just a curiosity. It's a powerful tool for ensuring effective protection. This brings us to a critical question. If sunscreens are designed to interact strongly with ultraviolet light, how do we measure and compare their effectiveness? The concept of sun protection factor, SPF, was developed by Franz Greiter in 1962, nearly 25 years after he created his first sunscreen. SPF specifically measures protection against UVB radiation, the primary cause of sunburn and a major contributor to skin cancer risk. The SPF number represents how much longer a person can remain in the sun before developing redness compared to having no protection. For example, someone who normally begins to burn after 10 minutes of sun exposure could theoretically remain in the sun for 150 minutes when properly using an SPF 15 sunscreen. 10 minutes times 15 is equal to 150 minutes. However, this straightforward multiplication is often misunderstood and can be misleading. SPF 15 blocks approximately 93% of UVB rays, SPF 30 blocks 97%, and SPF 50 blocks 98%. The protection does not increase linearly with the SPF number. The difference between SPF 30 and SPF 50 is marginal compared to the difference between wearing no sunscreen and wearing SPF 15. The SPF system has been tremendously valuable for public health, says Dr. Alicia Edwards, but it has significant limitations. It primarily measures protection against sunburn, which is caused mainly by UVB radiation. Until relatively recently, it told us little about protection against UVA radiation, which penetrates deeper into the skin and contributes significantly to photoaging and skin cancer risk. To address this limitation, regulatory agencies worldwide have developed additional standards for measuring UVA protection. In the United States, broad-spectrum designation indicates that a sunscreen provides UVA protection proportional to its UVB protection. The European Union uses a UVA circle logo when products achieve a UVA protection factor at least one-third of the labeled SPF. Japan and other countries use the PA+ rating system, PA+, PA++, PA+++, or PA++++, to indicate the level of protection against UVA. Testing sunscreens involves both in vitro laboratory and in vivo human subject methods. In vitro methods typically measure how much ultraviolet light passes through a standardized layer of sunscreen applied to a transparent plate or specialized tape. The dramatic visible/ultraviolet contrast we see in sunscreen photographs represents exactly what these instruments measure: the sunscreen's ability to block ultraviolet radiation while remaining relatively transparent to visible light. In vivo SPF testing involves applying a standard amount of sunscreen, 2 milligrams per square centimeter, to small areas on volunteers' backs, exposing these areas to increasing doses of simulated sunlight and observing when redness develops compared to unprotected skin. This process is strictly regulated and conducted under medical supervision to ensure participant safety. Few consumers realize that the SPF on the label is achieved only when applying the sunscreen at a thickness of 2 milligrams per square centimeter of skin, notes Dr. Ian Reeves. Studies consistently show that most people apply only 20 to 50% of this amount, which significantly reduces the effective protection. This underapplication problem is one reason why ultraviolet photography of sunscreen application has become an important educational tool. When people can actually see gaps in their sunscreen coverage, invisible in normal light but starkly apparent under ultraviolet, they tend to apply products more thoroughly. The dramatic appearance of sunscreen under ultraviolet light has practical applications beyond education and quality control. It has become a powerful visualization tool in dermatological research, helping scientists develop more effective protection strategies against the full spectrum of ultraviolet damage. Traditional sunscreens work by preventing ultraviolet radiation from reaching the skin, either by absorbing it or reflecting it away. But the frontier of sun protection science extends beyond simply blocking UV rays to addressing the damage that occurs despite our best preventive efforts. No sunscreen blocks 100% of ultraviolet radiation, explains Dr. Irene Reynolds, a photobiologist researching novel photoprotection strategies at the University of California, San Francisco. Even with perfect application of a high SPF, broad-spectrum product, some UV radiation reaches the skin. And other factors, free radicals, infrared radiation, visible light, can also contribute to photo damage through mechanisms we're only beginning to understand. This recognition has led to the development of photobiologically active ingredients that work differently from traditional UV filters. Rather than simply blocking radiation, these compounds interact with biological processes triggered by UV exposure. Antioxidants represent one major category in this approach. Ultraviolet radiation generates reactive oxygen species, ROS, in the skin, unstable molecules that damage cellular components including DNA, proteins, and lipids. Antioxidants like vitamins C and E, green tea polyphenol, and resveratrol can neutralize these ROS before they cause harm. We're seeing increasing evidence that adding antioxidants to sunscreens enhances their protective effects, says Dr. Reynolds. In some studies, the combination provides greater protection than would be expected from the SPF value alone. More revolutionary approaches include DNA repair enzymes encapsulated in liposomes that can penetrate the skin and help reverse UV-induced DNA damage. One product contains photolyase, an enzyme that specifically repairs thymine dimers, the primary form of DNA damage caused by UVB radiation. Originally discovered in organisms like algae that have evolved sophisticated UV protection, these enzymes can be delivered topically to enhance the skin's natural repair mechanisms. Other cutting-edge strategies focus on enhancing the skin's endogenous protective responses. Certain fern extracts contain compounds that stimulate the body's production of heat shock proteins and other protective molecules that help cells withstand UV stress. These biological response modifiers represent a fundamentally different approach to photoprotection, working with the body's natural defenses rather than simply creating a physical or chemical barrier. The future of photoprotection is not just about creating better barriers, Dr. Reynolds emphasizes. It's about understanding and enhancing the complex biological responses that protect us from radiation damage. The ideal approach combines prevention, interception of damage processes, and enhancement of repair mechanisms. These advanced photoprotection strategies may not create the same dramatic visual effect under ultraviolet light that traditional sunscreens do. Their action is more subtle, occurring at the cellular and molecular levels rather than at the skin surface. But they represent an important evolution in our understanding of ultraviolet protection. And this evolution continues to be guided by a phenomenon that became apparent in those first ultraviolet photographs of sunscreen: the remarkable efficiency with which certain molecules can interact with, absorb, and transform ultraviolet radiation. Despite their proven ability to prevent skin cancer and their striking effectiveness visible in ultraviolet images, sunscreens have become surprisingly controversial. Concerns about environmental impacts, potential health effects, and regulatory adequacy have created confusion among consumers and sparked debates within the scientific community. The environmental controversy erupted into public consciousness in 2015, when a study published in the Journal Archives of Environmental Contamination and Toxicology reported that oxybenzone, a common chemical sunscreen ingredient, could damage coral reefs even at extremely low concentrations. Subsequent research found that oxybenzone and several other organic UV filters may contribute to coral bleaching, disrupt marine life reproductive cycles, and accumulate in aquatic ecosystems. These findings led Hawaii to pass legislation in 2018 banning the sale of sunscreens containing oxybenzone and octinoxate, with the law taking effect in 2021. Other regions with coral reefs, including Palau, the U.S. Virgin Islands, Key West, and parts of Mexico, enacted similar bans. The environmental concerns are legitimate, acknowledges Dr. Amanda Evans, who studies the ecological impacts of personal care products. We're finding sunscreen ingredients in surface waters worldwide, and laboratory studies show they can affect aquatic organisms. But we also need to balance these concerns against the very real human health benefits of sunscreen use. This balance became even more complicated when questions emerged about the safety of certain sunscreen ingredients for humans. In January 2020, the FDA published a study in the Journal of the American Medical Association showing that 6 common chemical sunscreen ingredients, avobenzone, oxybenzone, octocrylene, homosalate, octisalate, and octinoxate, were absorbed into the bloodstream at concentrations exceeding the FDA's threshold for waiving additional safety testing. The presence of these compounds in blood does not necessarily indicate a safety risk, emphasizes Dr. Ian Reeves. But it does mean we need more research to understand their long-term effects, particularly since some of these compounds have shown endocrine-disrupting activity in laboratory studies. The FDA has responded to these concerns with regulatory changes. In 2019, the agency proposed a rule that classified zinc oxide and titanium dioxide, mineral filters, as generally recognized as safe and effective GRACE, while indicating that additional data were needed for 12 common chemical filters. 2 other ingredients, PABA and trolamine salicylate, were proposed to be not GRACE due to safety concerns. These regulatory shifts and scientific debates have created confusion among consumers, with some turning to natural or reef-safe products that may not provide adequate protection. This has concerned dermatologists, who worry that reduced sunscreen use could reverse decades of progress in skin cancer prevention. The perfect sunscreen would be completely safe for humans and the environment while providing complete protection against all wavelengths of harmful radiation, says Dr. Alicia Edwards. We haven't achieved that ideal yet, but the evidence remains clear. The risks of unprotected sun exposure far outweigh the potential risks of current sunscreen formulations for most people. The sunscreen controversy highlights a broader issue in science communication: how to convey nuanced risks and benefits to the public without creating undue alarm or complacency. Ultraviolet photography of sunscreen has become one powerful tool in this communication effort, providing visual evidence of protection that resonates more strongly than abstract discussions of SPF numbers or molecular mechanisms. When people see how completely a properly applied sunscreen blocks ultraviolet light, notes Dr. Edwards, it often cuts through the confusion and controversy. The image speaks directly to the fundamental purpose of these products, creating a shield against radiation we cannot see but that can seriously harm us. This brings us back to our original question: why does sunscreen look so weird in ultraviolet light? We now understand that this visual phenomenon is not merely a curiosity but a direct demonstration of the science behind photoprotection, a window into an invisible spectrum that shapes life on Earth, and a powerful reminder of our place in a universe filled with radiation both beneficial and harmful. The story of sunscreen and ultraviolet light is ultimately a story about our relationship with our parent star. The sun bathes Earth in radiation across the electromagnetic spectrum, from radio waves to gamma rays. Our atmosphere filters much of this radiation, creating a habitable environment where life could evolve. But significant amounts of ultraviolet light still reach the surface, creating both opportunities and challenges for terrestrial organisms. We evolved under the sun and are fundamentally adapted to its radiation, reflects Dr. Isaac Richards. Our bodies need sunlight to produce vitamin D, set our circadian rhythms, and maintain psychological well-being. But we also need protection from its more energetic wavelengths. This dual nature of sunlight, both essential and potentially harmful, has shaped the evolution of life on Earth. The appearance of sunscreen under ultraviolet light visualizes this complex relationship. The stark black or reflective white of sunscreen-covered skin against the fluorescent glow of unprotected skin highlights the boundary between our natural state and our technological intervention. This visualization also connects to broader questions about human evolution and adaptation. As humans migrated out of Africa into regions with less intense sunlight, skin pigmentation decreased to allow sufficient vitamin D production. These evolutionary adaptations occurred over thousands of generations. Now, with rapid global travel and migration, many people live in environments for which their skin pigmentation is not evolutionarily optimized. Sunscreen represents a technological solution to an evolutionary mismatch, explains Dr. Andrea Evans. Fair-skinned individuals in tropical environments or darker-skinned people in northern latitudes both face challenges that their natural pigmentation isn't optimized to handle. Sunscreen and vitamin D supplementation allow us to thrive in environments very different from those our ancestors adapted to. This technological mediation of our relationship with sunlight extends beyond Earth. As humans contemplate long-duration space missions and potential settlement of other worlds, protection from radiation becomes even more crucial. Mars, lacking Earth's protective magnetic field and thick atmosphere, receives significantly higher levels of ultraviolet and cosmic radiation at its surface. The strategies we've developed for ultraviolet protection on Earth will inform how we protect ourselves on other planets, notes Dr. Richards. The fundamental chemistry and physics remain the same, though the specific challenges may differ. The appearance of sunscreen under ultraviolet light would be just as striking on Mars as it is on Earth, perhaps even more so given the different radiation environment. This cosmic perspective reminds us that our existence is intimately connected to the stars. The elements in our bodies and in our sunscreens were forged in stellar furnaces billions of years ago. The ultraviolet light we protect ourselves from is generated by nuclear fusion in the sun's core, traveling 93 million miles to reach us in just over 8 minutes. The weird appearance of sunscreen under ultraviolet light is thus not merely a chemical curiosity or a social media phenomenon. It is a visualization of our place in the cosmos, creatures evolved under a particular star, using the elements of the universe to protect ourselves from the very radiation that makes life possible. Beyond the physics, chemistry, and biology lies perhaps the most important aspect of this story: the human element. Sunscreen is not just a scientific achievement. It is a public health intervention that saves lives, prevents suffering, and allows people to enjoy outdoor activities safely. The visual drama of sunscreen under ultraviolet light has become a powerful educational tool precisely because it connects abstract scientific concepts to personal health decisions. When people see the stark contrast between protected and unprotected skin, the invisible becomes visible, and the importance of proper sun protection becomes tangibly real. I've had patients who were resistant to using sunscreen regularly until I showed them these ultraviolet images, says Dr. Alicia Edwards. Seeing is believing. When they visualize how completely sunscreen blocks harmful radiation, something clicks that didn't connect when I just explained the science verbally. This visualization has particular importance for populations most vulnerable to sun damage. People with naturally fair skin, those with conditions like albinism, individuals taking photosensitizing medications, and people with genetic disorders like xeroderma pigmentosum face significantly higher risks from ultraviolet exposure. For these individuals, effective sunscreen use is not merely about preventing premature aging or reducing cancer risk. It can be essential for basic quality of life. Isabella Richards was diagnosed with xeroderma pigmentosum, XP, at age 3. This rare genetic disorder prevents her body from repairing DNA damage caused by ultraviolet light. Without rigorous protection, she would develop severe sunburns, rapid skin aging, and a dramatically elevated risk of skin cancer, potentially thousands of times higher than the general population. Sunscreen is not optional for me. It's survival, Isabella explains. When I see ultraviolet photographs showing how sunscreen creates this perfect black shield, that's not just interesting science to me. It's a visualization of my shield against a world that would otherwise be incredibly dangerous. For Isabella and others with XP, understanding precisely how sunscreens work and visualizing their effectiveness is crucial for managing daily life. The striking appearance of sunscreen under ultraviolet light provides both reassurance and motivation to maintain vigilant protection. Even for those without such extreme sensitivity, the visualization of sunscreen effectiveness can transform sun protection from a chore into a comprehensible act of self-care. It connects abstract risk reduction to a concrete, visible phenomenon. There's something powerful about seeing the invisible made visible, notes Dr. Amanda Edwards. It's one thing to understand intellectually that ultraviolet radiation is hitting your skin. It's another to actually see its effects and the protection sunscreen provides. The weird appearance of sunscreen under UV light bridges the gap between abstract knowledge and personal experience. This connection between the scientific and the personal reminds us that even the most sophisticated understanding of photoprotection ultimately serves a human purpose, allowing people to live healthier, more comfortable lives in relationship with their environment. The striking visual phenomenon of sunscreen under ultraviolet light thus becomes not just a scientific curiosity but a portal to deeper understanding of our place in the world. We began with a simple question. Why does sunscreen look so weird in ultraviolet light? Our exploration has taken us from the quantum mechanics of light absorption to the cosmic origins of radiation, from ancient microbial adaptations to cutting-edge nanotechnology, from cellular biology to public health policy. The answer, we now understand, lies in the fundamental interaction between matter and energy. Specifically, the ability of certain molecules to selectively absorb or reflect radiation of particular wavelengths. Sunscreen appears black or reflective white in ultraviolet photographs precisely because it is doing its job, preventing harmful radiation from reaching our skin by either absorbing it or bouncing it away. This visual phenomenon reveals something normally invisible, making tangible a protection process that otherwise occurs beyond our perceptual reach. It transforms an abstract scientific concept into a striking visual experience that resonates even with those who have little interest in photochemistry or dermatology. But perhaps the most profound aspect of this exploration is how it highlights the selective nature of all human perception. We experience only a tiny slice of reality directly. The vast majority of the electromagnetic spectrum, from radio waves to gamma rays, exists beyond our natural senses. Our understanding of these invisible realms comes through technology that extends our perceptual abilities and through scientific frameworks that help us interpret what we cannot directly experience. Sunscreen under ultraviolet light offers a glimpse into this broader reality. A reminder that the world is far richer and more complex than what we can see with our eyes alone. It makes visible the invisible boundaries between protection and vulnerability, between technology and nature, between the radiation that sustains us and the radiation that harms us. In this sense, the weird appearance of sunscreen under ultraviolet light is more than just an interesting visual effect or a demonstration of photochemistry. It is a window into the limited nature of human perception and the remarkable ways we have developed to protect ourselves from dangers we cannot directly perceive. As we apply sunscreen before heading outdoors, that invisible shield now carries deeper meaning. A testament to human ingenuity in the face of cosmic forces, a visualization of protection against invisible threats, and a reminder that sometimes the most important boundaries are the ones we cannot see without special assistance. In a universe filled with radiation both beneficial and harmful, we have learned to create shields from the very elements forged in ancient stars. And in the striking images of those shields under ultraviolet light, we glimpse a profound truth. Our most essential protections often operate in realms invisible to our limited human senses, yet their effects can mean the difference between damage and safety, between illness and health, between vulnerability and security in our dance with the sun.